Hello friends, welcome to YouTube channel Electronics. In this video, we learn ADC and DAC, analog to digital converter and digital to analog converter. First of all, let's briefly know about analog and digital signals. Analog signals are continuous waves and vary smoothly over time. Analog signals can provide an infinite number of different voltage values. On the other hand, digital signals are discrete signals, only have two states, logic 1 and logic 0. Here this ADC stands for analog to digital converter that can convert analog signals into digital signals. There are mainly 5 types of ADC circuits are used. Similarly, this DAC stands for digital to analog converter that can convert digital signals into analog signals. Weight resistor and R2R ladder circuits are the two most commonly used DACs. The electronic gadgets and systems that we are using in our daily life contains ADC and DAC circuits inside them. Let's take an example of a smartphone. Whenever we are streaming a music video on our smartphone, then this digital bit stream is converted into the electric signal, and through the smartphone speaker and display we can enjoy this music video. Here the DAC inside the smartphone converts the digital bit stream into the analog signal. Similarly, when we are talking on the smartphone, the microphone converts our voice into electric signal, and the ADC inside the phone converts this analog signal into digital signal, and the mobile's antenna transmits this signal in the form of radio waves. So these ADC and DAC circuits are an integral part of the electronic gadgets that we are using in our daily life. Now the question arises, why we need to convert the signals from analog to digital and digital to analog? Here is the answer. Most of the physical signals which we find around us are analog in nature. For example, temperature, sound, pressure, touch and etc. And by using a transducer, we can convert these physical signals into electrical signals. The common examples of a transducer are microphone, loudspeaker, thermometer and etc. But these analog signals have many disadvantages, particularly when they are used in communication. First one, they are very susceptible to interference from outside sources such as radio waves, lightning strikes and etc. Additionally, they are not very efficient at storing large amounts of data, since each individual value has to be stored separately. Furthermore, since the maximum and minimum values of an analog signal cannot be easily determined without special equipments like oscilloscopes and frequency analyzers, so it is very difficult to process them accurately. Hence, these are the three main disadvantages of analog signals. On the other hand, digital signals are very less susceptible to the noise, because noise is usually much smaller than the amplitude of a pulse. Additionally, digital signal processing is more flexible and secure, because digital information can be easily encrypted and compressed. Furthermore, digital signals can be easily stored on any magnetic media or optical media using semiconductor chips. Hence, these are the three main advantages of digital signals over analog signals, and that is why the analog signals are converted into digital signals so that they can be easily processed and stored. So whenever it is required, then using DAC, it is possible to retrieve these signals. But these type of conversions are not lossless, because during the conversion some information will be lost. It is because if we observe an analog signal, it is continuously varying in amplitude along with time. But the digital signals have two discrete values of high and low along with the time. For example, if this analog signal is varying in 0 to 5 volts range, then it can take any value between this 0 to 5 volts. Therefore, the resolution of the analog signal is infinity. But if we convert this into digital signal, then then it will have only two values, 0 volts or 5 volts. So it is discrete in time as well as in amplitude. So to understand how the analog signals is converted into digital signals, let's see the steps involved in analog to digital conversion. The steps are sampling, quantization and coding. Apart from these steps, we must also consider Nyquist theorem and Aliasing effect. We will discuss them one by one. First one, sampling. This process involves taking samples of an analog signals at specific points of time to create discrete signals. The number of samples taken per second is called the sampling rate. As we can observe here that the higher the sampling rate, the more accurately we can represent the analog signal. In ADC, the sampling rate is the key factor. According to Nyquist sampling theorem, the signal should be sampled at least twice of the analog signal's bandwidth to prevent the loss of data. So for a sine wave with maximum frequency of fmax, the minimum sampling rate should be equals to 2 times fmax. For example, if the analog signal's maximum frequency is 2 kHz, then the minimum sampling rate must be 4 kHz. Likewise, if the maximum frequency of an analog signal is 4 kHz, then the sampling rate must be at least 8 kHz to prevent the losses in analog to digital conversion. For example, if we didn't consider the Nyquist theorem and kept the sampling rate is less than 2 times fmax, like here in this example, then the frequency of the reconstructed signal will be less than the original signal. This type of error is called aliasing effect. So to avoid this type of error or aliasing effect, we must follow the Nyquist theorem. That means the sampling rate must be greater than or equals to 2 times of the maximum frequency. Now let's observe what happens when the input signal is a square wave. Suppose the frequency of this square wave is f0. According to Nyquist theorem, we are sampling this square wave with a sampling rate more than 2fo so that we can be able to reconstruct the same square wave. But as we know that the square wave contains harmonics apart from its fundamental frequency. Hence, due to this harmonics, no matter what is the sampling rate may be, the aliasing effect will occur in the reconstructed signal. And to avoid this aliasing effect, we need to use anti-aliasing filter before applying square wave to ADC. This anti-aliasing filter is basically a low pass filter. For example, if the maximum sampling rate of the ADC is fs, then the cutoff frequency of this anti-aliasing filter must be equals to fs by 2 so that we can remove the harmonics in square wave input. Hence, we can reduce the aliasing effect. So before sampling, the square wave signal input must pass through this anti-aliasing filter. This is how the sampling is done in ADC. Now the next step, quantization. It is a crucial process in analog to digital conversion. After the analog signal is sampled at regular intervals, then the sampled values are matched with the closest values of the discrete levels. This process of converting analog signals sampled values to discrete digital values are called quantization. Here we can observe that the sampled analog signal is quantized into 16 different levels and each sampled value is assigned to a nearest value in these 16 levels. For example, this sampled value is in between discrete values 5 and 6. Here this sampled value is rounded off to the nearest value, that is value 6. But this rounding off process introduces a quantization error, which is the difference between the actual analog input value and the round off quantized digital value. This quantization error can be limited by increasing the number of discrete levels or bits in quantization process. The more quantization level we use, the lesser the quantization error. The number of quantization bits or levels determines the resolution of the ADC. So the resolution of an ADC is its ability to detect the smallest input signal change and representing that smallest change in the digital output. So for a given ADC, if the resolution is n bits, then in a binary number system, the total number of discrete levels is equal to 2 to the power of n. For example, if an ADC have the resolution of 3 bits, then the input signal will get quantized into 2 to the power of 3 levels, that is 8 levels. And in terms of voltage, the resolution can be defined as the full scale range of the ADC divided by the 2 to the power of the total number of bits, where the full scale range can be written as V maximum minus V minimum. For example, for a 3-bit ADC, if the full scale range is 10 volts, then the resolution of the ADC is equals to 10 volts divided by the 2 to the power of 3, that is equals to 1.25 volts. That means the minimum change in sampled value input which can be detected by the ADC is equals to 1.25 volts. So if the change in the sampled value is less than 1.25 volts, then this ADC unable to detect that change. Here the undetected sampled values are rounded off to the nearest values. If the full scale range of a 3-bit ADC is 2 volts, then the resolution of the ADC becomes 2 volts divided by 2 to the power of 3, that equals to 0.25 volts. So now the minimum change which can be detected by the 3-bit ADC is equals to 0.25 volts. So in this way, by changing the full scale range voltage, the minimum detectable voltage of the ADC can be decreased. Hence the resolution of the ADC increases. But here the disadvantage is that the conversion range of the ADC is reduced. So we have to trade off between resolution and full scale range. The solution for this trade off is by keeping the same reference voltage. If we increase the number of bits, like here 8 bits, we can increase the resolution. Here the resolution becomes 10 volts divided by 2 to the power of 8. That equals to approximately 39 millivolts. So now this 8-bit ADC able to detect the change in sampled value of even 39 millivolts. Hence by increasing the number of bits, we can increase the resolution of an ADC. Let's prepare a transfer function graph of a 3-bit ADC with full scale range of 1 volt. Here our resolution equals to FSR 1 volt divided by number of bits, that is 3 bits. So 2 to the power of 3, that equals to 1 volt divided by 8. Hence the resolution is 0.125 volts. So in x-axis we can represent FSR like this: 1 by 8, 2 by 8 and so on up to 8 by 8. Ideal transfer function of an ADC looks like a straight line. That means if the resolution of the ADC is infinite. But here the resolution or minimum detectable voltage is equals to 0.125 volts. So the actual transfer function of this 3-bit ADC looks like a staircase. Let's clearly discuss this staircase like structure of transfer function with this diagram. As we know, ideal transfer function is a straight line. But because of 0.125 volt resolution, the sampled signal is quantized in 8 levels and each sampled value is round off to nearest level. Like here, these two values are considered as 0 and these two values are considered as 0.125. So up to second sampled value, the transfer function is 0. At the second sample, it rises to 0.125 volts and then it steps up to 0.250 volts. Next sampled value is round off to 0.25 volts. Then again it steps up to 0.375 volts. So our actual transfer function looks like a staircase. Hence due to quantization process, the error will be introduced in the output of the ADC. This error is known as the quantization error. This quantization error can be defined in terms of LSB. Generally, irrespective of the number of bits and the reference voltage, the quantization error will be equals to 1 LSB, because if you observe over here, each step corresponds to 1 LSB. Of course, we can reduce this quantization error by increasing the number of bits. For example, by using an 8-bit ADC instead of 3-bit ADC, we can reduce the quantization error. And also, Just by shifting the transfer function to the left, we can reduce the quantization error. Now the quantization error changed from 1 lsb to 0.5 lsb. To understand this, let's simplify this x-axis voltage levels. Just write the x-axis voltage levels in the form of natural numbers 1, 2, 3, 4 and so on. Now if you observe over here, whenever the input voltage is in between 0 to 0.5 volts, then the output of the ADC is equals to 0, 0, 0. The ADC output changes whenever the input voltage goes above the 0.5 volts. Now the maximum possible error in the ADC output reduced from 1 volt to 0.5 volt, or we can say that the error is reduced to 0.5 lsb. This is all about quantization. Now let's see the overall block diagram of ADC. Let's briefly discuss each block. At first, the input analog signal is sampled at different intervals according to the sampling rate. Next, this whole circuit holds the sampling output at the same value until the next sample is taken. This is because in reality, ADC takes some time to quantize the sampled signals. In next step, the sampled values are quantized by converting them into discrete digital values. Then this encoder converts the quantized values into digital signals. So these are the basic steps in analog to digital conversion process. Now let's see how this simple 2-bit ADC works. For simplicity, we will assume that the analog input Vin is in between 0 to 4 volts. So we have set of V reference 4 volts. Because of this V reference, the voltage divider network will drop voltages across each its nodes like this: 1 volt, 2 volt and 3 volts respectively. Suppose if this analog input voltage level is 2.5 volts, then this 2.5 volts level appears across inverting input of these three comparators. Here we can say that U1 and U2 comparators inverting input is high. It is because the reference voltage of 1 volt and 2 volt at non-inverting input is lesser than 2.5 volts of analog input level. But U3 comparators non-inverting input is low because 3 volts reference voltage at inverting input is greater than 2.5 volts of analog input level. Here these comparators compares the input voltage level. If the Vin is lesser than V reference, the output is off, and if Vin is greater than V reference, the output will on. So here U1 and U2 comparators will be on while U3 comparator is off. These output levels are fed to the XOR gate. As per XOR gate logic, whenever input levels are different, then its output is on, otherwise output is off. So only the middle XOR gate is on while the other two are off. This XOR gate's output is fed to the diodes. Here D2 diode's anode gets positive voltage level, hence it is forward biased, so it is on and makes Q1 digital output high state, while the rest of the diodes getting negative voltage level at their anodes, so they are reverse biased, hence they are at off state. So Q0 digital output is at low state, hence the value of analog input signal Vin determines the functioning of this circuit. The resolution of this 2-bit ADC is 1 volt. If we want to increase the resolution, we must use 3-bit ADC using more comparators. Then the resolution increases to 0.5 volts. Now let's briefly discuss about the digital to analog converter. Here, according to digital input bit stream, analog signal is generated. There are mainly two types of DACs are used: weight resistor DAC and R2R ladder DAC. Let's discuss how a DAC works by taking an example of 4-bit weight resistor DAC. This method utilizes the summing operational amplifier circuit. It adds the input signal with different gains corresponding to their resistors. Just label the 4 summing inputs V0, V1, V2 and V3 and keep the RF value as 1 kilo ohm and set the input resistance value from V3 to V0 as 1 kilo ohm, 2 kilo ohm, 4 kilo ohm and 8 kilo ohm respectively. Here we have double the input resistance value in each step. This is nothing but doubling the weight of each input with respect to the next input. So here we end up with 8421 binary code ratio corresponding to 2 cube, 2 square, 2 to the power of 1 and 2 to the power of 0. If we apply a 4-bit digital input LSB at V0 and MSB at V3, we will get corresponding analog signal at the output. Let's see how this circuit works. As we know that inverting op-amp circuit, Vout is given as minus Rf by Rin into Vin. So in this inverting summing amplifier, the output voltage Vout is nothing but sum of the each input voltage multiplied by its corresponding gain. For a 4-bit DAC, we can apply binary input ranging from 4 zeros to 4 ones, which corresponds to 16 possible combinations. If logic 0 is applied at all 4 inputs, then this Vout equation gives result 0. So the analog output voltage is also 0. If we apply TTL voltage of plus 5 volts or logic 1 at the V0 input or LSB, then accept this, rest of all the equation gives 0 result. So now Vout is equal to minus 1 kilo ohm divided by 8 kilo ohms multiplied with 5 volts. That equals to minus 0.625 volts. Hence the 4-bit binary code 0001 produces an output voltage of minus 0.625 volts. Likewise, if we apply logic 1 to the summing amplifier's V1 input, then only this part of the equation provides result. Rest of all gives 0. So now Vout equals to minus 1 kilo ohm divided by 4 kilo ohms multiplied with 5 volts. That equals to minus 1.250 volts. So the 4-bit binary code 0010 produces an analog output voltage of minus 1.25 volts. Again, with logic 1 applied to the summing amplifier's V2 input, then only this part of the equation gives the result. So Vout equals to minus 1 kilo ohm divided by 2 kilo ohms into 5 volts. That equals to minus 2.5 volts. Hence the 4-bit binary code 0100 produces an analog output voltage of minus 2.5 volts. Finally, if logic 1 is applied to the summing amplifier's V3 or MSB input, then only this part of the equation provides result. So Vout equals to minus 1 kilo ohm divided by 1 kilo ohm multiplied with 5 volts. That is nothing but minus 5 volts. So this 4-bit binary code of 4 ones produces an analog output voltage of minus 5 volts. This is how this circuit generates analog output corresponding to the input digital bits. Here this inverting op-amp summing amplifier Vout equation can be considered as minus of 1 into V3 plus 1 by 2 into V2 plus 1 by 4 into V1 plus 1 by 8 into V0. If we observe this equation closely, this part 1 by 8 V0 contributes least value to the output. Hence this is the LSB, that is 1 by 8 into 5. That equals to 0.625. Here this 0.625 volts equals to 1 bit change in the binary number. This value is nothing but resolution of 4-bit ADC. Here in this table we can see how the analog output voltage changes with the digital input bits ranging from 4 zeros to 4 ones. Here we can notice that an output voltage change of 0.625 volts per 1 bit change in digital input. This timing diagram shows the output sequence of the 4-bit DAC. It can be observed that the output voltage of the DAC varies from 0 volts to its maximum negative voltage as the digital input bits increases sequentially. Now by increasing the number of bits and the resistive summing network, we can increase the resolution of the analog output voltage. For example, A 4-bit DAC provides resolution of 0.625 volts, but an 8-bit DAC provides resolution of 0.039 volts per 1 bit change in digital input. Here in this timing diagram, we can compare the output response of a 4-bit and 16-bit DACs. Because of greater resolution of 153 microvolts, the output of a 16-bit DAC looks like a pure sine wave. So by improving the resolution, we can improve the accuracy of a DAC. These are the important parameters of ADC and DAC: resolution, full scale range, sampling time, conversion time, gain error and offset error, non-linearity, and total harmonic distortion. We will discuss these parameters clearly in upcoming videos. ADCs have a wide range of applications in various fields such as PLCs, control systems, smartphones, audio-video devices, and etc. Likewise, DACs also have many applications. They are commonly used in digital printers, measuring instruments, digital motor control, audio-video devices, and etc. That's all about ADC and DAC. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.